Good morning, everyone. It's good morning. Shall we begin the session? Yes, today's topic is chapter number 5, CPU scheduling. How CPU scheduling is done on the basis of the multi-program operating system that switches the CPU among various processes, right? Okay. So CPU scheduling is one of the basis of the multi-program operating system, and by switching the CPU among the various processes, the operating system can make the computer more productive. And in this chapter, we introduce the basic CPU scheduling concepts and also presents the various CPU scheduling algorithms like shortest job pass first come first serve. So in chapter number 4, we are introducing the threads and also the kernel threads, not the process thread, that in fact by scheduling these are done for the operating system, but when we talk about the term process scheduling and the thread scheduling, they are often interchangeable. So to introduce CPU scheduling, which is a basis for multi-program operating system, to describe various CPU scheduling algorithms, and to discuss the elevation or evaluation criteria for selecting a CPU scheduling method that is available, that is used with the installation that is used with the CPU scheduling algorithm for a particular system. Now, what are the various basic concepts? So in the basic concepts, it is used with the single processor system. Only one processor or only one process can run at a time. Yes, hi Joseph, how are you?
I'm fine, sir. Good day, sir. Hello, sir. Let me just about the earpiece. Good day, sir. Tell me. Ma, what about the earpiece?
Hello. Yes, I'm not able to hear
Hi,
you,
sir.
Joseph. Hello.
Can you hear me, sir?
Are you able to hear me?
I can hear you. Hello, sir. Hello, sir.
But I'm not able to hear you. Please check your
Can you hear me
connections.
now, sir? Can you hear me now? Can you hear me now, sir?
Hello. Is that okay? Hello,
Can you
hello.
hear me now, sir? Can you hear me now?
So let's begin with the basic concept
Hello,
that
sir.
is used. So what is a CPU scheduling? One is a rescheduled, how the CPU rescheduled the concept, and the basic or the main objective of this that it is wait until the CPU is free and can be rescheduled. What is the main objective or what is the main concept that is used over here? So main objective of multi-programming is to have some process that is running at all the times to maximize the CPU utilization. And the basic idea is very simple. Whenever we are using the processes, whenever one process is executed until it must wait for the completion of some input output resources. And all this waiting time is wasted, no user work is accomplished. And with the multi-programming, we try to use this time productivity, and multiple processes are kept in memory at one time. And one process, yes, when one process has to wait, the CPU has to schedule for the another process. That means no two processes are executed at the same time. One process have to wait for the another process to be executed. The next is a scheduling of this kind is very fundamental operating system function, and almost every computer science resources are scheduled before the use, and CPU is of course one of the primary computer resources. Therefore, its scheduling is central to the operating system, because one of the aim is to use the operating system, that is scheduling the operating system or schedule the operating system, because it is one of the central aim for this. Then CPU input output bus cycle. So success of the CPU or the success of the bus cycle, that depends on the observed property of the various processes. And then there is a process execution that consists of a cycle, that consists of a CPU execution and the input output wait. When process alternate between these two states, process execution begins with the CPU burst, that is followed by the input output burst, which is followed by the another CPU burst, then another input burst, and so on. That means one of the process must wait for the another that is available with the CPU bursting time. And the duration of the CPU burst must have measured extensively. That means it is used in a very lethargical manner, although they vary greatly from process to process and from computer to computer. They tend to have frequency curves similar to the that is shown over here. This is 5.2 that is shown. This is wait for input output. This is wait for input output, then load the store and add the store read from file. This is the CPU burst. This is the input output burst, CPU burst, input output burst, CPU burst, and the input output burst. This is the histogram that is available for the CPU, that is available for the data that is available in this one. Then CPU scheduler. Whenever the CPU becomes idle, that means free, the operating system must select one of the processes in the ready queue to be executed. That means if there are 4 processes, one in the ready queue that is to be executed, so that is scheduled by the scheduler, that is used by the scheduler, that is available with the CPU burst. Now one is a preemptive scheduling. So next one is a primitive scheduling. So CPU scheduling decisions may take place under the 4 circumstances when a process switches the running to the waiting state. For example, as a result of the input-output request or the invocation of the wait for termination of one of the child processes. Then, when a process switches from the running state to the ready state, that is used. For example, that is when an interrupt occurs. So one is switching from one state to the another state. One is switches from the running to the ready state. Then switches from the waiting to the ready state whenever there is a completion of the input output, and at last when a process terminates. And for the conditions 1 and 4, there is not choice in terms of scheduling. A new process must be executed or must be selected for the execution. So when there is no choice, that is known as a non-primitive or the cooperative. Otherwise, it is primitive. Once the CPU has been allocated to processes, the CPU keeps the process or CPU until it reaches to the CPU, either by terminating or by switching to the waiting state. This scheduling algorithm method are used by the Microsoft Windows Linux. that introduced the primitive scheduling and all the subsequent versions of the Windows operating system that we use, that are using the primitive scheduling. And the Mac operating system or the Macintosh also uses the primitive scheduling. Previous versions of the Macintosh operating system that works in the cooperative or the cooperative schedule. And unfortunately, primitive scheduling incurs a cost associated with the access to shared data. And while one is uploading the data, it is streamed so that the second one can run. And the same condition is uploaded or same will be used in such situation. We use the mechanisms. That is used to coordinate with the shared data. In the same way, when we talk about the primitive scheduling that is available, so this primitive scheduling also affects the design of the operating system kernel. That is basically an activity of the behalf of the process. And such activities may involve changing the important kernel data. Primitive in middle of the changes, and the kernel needs to ready for the modification of the data. So whenever we see about the permission, that also affects the design of the operating system kernel. And during the processing of a system call, the kernel may be busy with an activity on behalf of the processes. Such activity may involve changing kernel data. And what happens if the process is primitive in the middle of the primitive means finish in the middle of the changes that needs to read or modify the same structure. Cheers ensures, but the certain operating system includes most version of the Unix that deals with this problem by waiting either for a system call to complete or for input-output block to take place during or before doing a business. And this scheme ensures that the kernel structure is very simple, since the kernel will not preempt a process, but with the kernel data structure are in a consistent state. And unfortunately, they are using the kernel model that is a poor one for supporting the multitasking. Then there's the dispatcher. Another component that is involved in the CPU scheduling function is a dispatcher, and this is a module that gives control of the CPU to the process selected by the short-term scheduler, and this involves the following methods. One is the switching context, then switching to the next user mode, then jumping to the proper location in the user program to restart a program. To restart that program, we are using the jumper, we are using the dispatcher. So this gives control to the CPU whenever we are using or whenever we are starting with the process. And dispatcher should be as fast as possible, since it is invoked during every process switch. That is known as a switching or dispatch latency. Now, next is the scheduling criteria. The different CPU scheduling criteria have different properties, and the choice of a particular that is favored from one process to another process. And when we want to choose which algorithm we'll use, we must consider the properties of various algorithms that is used with the CPU scheduling algorithms. So criteria must include the following. One is the CPU utilization. So we want to keep the CPU as busy as possible, and conceptually the CPU utilization can range from 0 to 100%. And when you say about the real-time systems, it should range from 40% to the 90%. That is from the 40 to the 90%. The next is the throughput. So if the CPU is busy executing the processes, then the work is being done. That means everything is done, or every process is being done over here. That is the throughput. And for long processes, this rate may be the 1 process per hour. For short transactions, it may be 10 processes per hour. The next is the turnaround time. From the point of the view of a particular process, the important criteria is that how long it will take to execute that process. And the interval from the time of submission of a process at the time of the completion is turnaround time. So whatever the time that is used, that is the turnaround time. That is what is the waiting to get into the memory, waiting in the ready queue, executing on the CPU, and doing the input output. Next one is a waiting time. So what is the waiting time? That is the sum of the period spent waiting in the ready queue that is available. The next is the response time. That may be the best criteria for the response, and once a process can produce some output fairly early or early can produce computing new results while the previous results are being output to the users. Therefore, another measure is the time from the submission of a request until the first response is produced. And this measure called known as the response time. It is the time that it takes to start the responding, not the time it takes to respond to the or output to the response. And it is desirable to maximize the CPU utilization and throughput and to maximize the turnaround time, waiting time, and the response time. And in most of the cases, we optimize the average measure. However, under some circumstances, it is desirable to optimize the minimum or the maximum values rather than the average. Now, next is the scheduling algorithms. What are the various scheduling algorithms? The CPU scheduling deals with the problem of deciding which of the processes in the ready queue is to be allocated the CPU, and there are many different CPU scheduling algorithms. In this section, we describe several of them or some of them. So as the name advises, it is first come first serve scheduling algorithm. This is used for the data with this scheme. The process that requires the CPU is first allocated to the CPU first. And the implementation of the first come first serve policy is decided. It is easily managed with the FIFO, that is first in first out. And when the process enters the ready queue, the PCB is linked to the tail of the queue. So when the CPU is free, it is allocated the data, it is allocated the memory to the CPU data. The average waiting time under the first come first serve policy is quite often long. And when we say about the set of the processes that arrive at time 0 with the length of the CPU burst given in the milliseconds. This is the process, this is the burst time, this is P1, P2, P3, 24, 3, 3. And if the processes arrives in the order P1, P2, P3 and are served in the first come first serve order, we get the result that is shown in the following Gantt chart. This is 0 to 24, then 3, 27, then 3, 30. So the waiting time is 0 milliseconds for the process P1 and 24 milliseconds for process P2, 27 milliseconds for P3. In the same way, average time is taken out by adding both divided by 3. So if the process arrives in the order P2, P3, P1, the result will be shown in the following Gantt order. So first is P2, then 0, after this there are 3, then 6, 3 plus 3 is 6, because P3 is taken as a 3, then there is a 24, that is 30. Now the waiting time of P1 is 6 seconds and P3 is 0, 3, P2 as a 3. Then shortest job first scheduling. So different approaches to the different CPU scheduling is the shortest job first scheduling. That means this algorithm associates with each process the length of the process next CPU burst. That means what is the length of the process that is next to the CPU burst. And whenever the CPU is available, it is assigned to the process that has the small next CPU burst. And if the next CPU burst of two processes are the same, so first come first serve scheduling is used to break the tie. Note that a more appropriate term for this scheduling method would be the shortest next CPU burst algorithm, because scheduling depends on the length of the next CPU burst of a process rather than its total